Hello students. Till now our discussions were focused towards electric field intensity, electric flux density and the applications of those, right? Now from this session onwards our focus shifted towards magnetic field and magnetic flux density and its applications. Okay, keep that in your mind. Till now whatever the discussions we were done were towards the electric field and its applications. From now onwards we are switching on to the magnetic field concepts. Okay, so the first concept is how the magnetic field develops. Okay, so tell me how a magnetic field develops around a material. So what is magnetic field actually? So magnetic field is the effect of flow of current through a conductor. Magnetic field is the effect of flow of current through a conductor. That means we can call it as a cause and effect. The cause is flow of current through a conducting material and its effect is magnetic field, production of magnetic field around the vicinity of that particular conductor, right, in a region. You can ask a question. So how a magnetic field develops inside a permanent magnet, around the permanent magnet. So whether the current is flowing inside the permanent magnet or not. So you should ask that question. Yes, obviously there is a flow of tiny currents inside the permanent magnet. That's why it creates a magnetic field around it. Okay, so magnetic field never exists where there is no current flow. Okay, keep this in your mind. Now in order to analyze, in order to use magnetic field in our electromagnetic wave theory, we need to adopt some principles, working principles and laws or theorems. So under such circumstance, the first law we are going to study under magnetic field is Biot Savart Law. Before going to Biot Savart's law, let me tell you what do you mean by magnetic field intensity and magnetic flux density. Okay, so the first thing is, let me write here, magnetic field is produced by the flow of current through a conductor. Therefore, flow of current is a cause and magnetic field is its effect. Both flow of current and magnetic field will be called as cause and its effect. Now, with respect to this, let us define magnetic field intensity and magnetic flux density. Magnetic field intensity and flux density. Field intensity is represented by symbol H. It is a vector. Magnetic field intensity is a vector represented by symbol H. Flux density is also a vector represented by symbol B. These two are with respect to magnetic field intensity symbol is H. Magnetic flux density, the symbol is B. So magnetic field intensity unit is ampere turns per meter. This is Tesla. 1 Tesla is equal to Weber per meter square. This is the unit. Okay. Unit of the flux density is Tesla, which is also referred as Weber per meter square. Clear? Okay. So this is the symbol for field intensity, magnetic field intensity and flux density. Then relationship between these two is, the relationship between these two is B is equal to mu into H. Mu into H, where mu is permeability of the medium, where mu is the permeability of the medium. If vacuum, then it is mu naught. Mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. This is the unit of this. Okay. So if mu is the permeability of the medium, then the medium is vacuum, then mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. This is the unit of this permeability. This is the relationship between magnetic flux density and magnetic field intensity. Previously what we have discussed is electric field intensity, electric flux density D is equal to epsilon naught into E. This is the relationship we have derived, right? What is D? Electric flux density. What is E? Electric field intensity. What is epsilon naught? Permittivity. Here B is magnetic flux density, H is magnetic field intensity and mu is permeability. These two are equivalent actually. Okay, you need to keep this equation in your mind. Now coming to the next part, what do you mean by uniform magnetic field and non-uniform magnetic field and steady state magnetic field? Let me define. If the flow of current, and its strength or magnitude is uniform, then magnetic field is uniform. In other words, we can say if the flow of current is uniform, we can say magnetic field is uniform. Also, we know that magnetic field is characterized by two parameters. One is strength or magnitude, and direction, because it is a vector. These are the two parameters we need to consider. A magnetic field intensity H is a vector which has two components, which is characterized by its magnitude and direction. In other words, we can say if a magnetic field intensity is constant with respect to its magnitude and direction in a particular region, then it is uniform magnetic field. If it is not constant, if it is continuously varying with respect to direction or magnitude at any point in a given region, then it is called as non-uniform magnetic field. Let me repeat again. If the direction and magnitude of a obtained magnetic field is constant is uniform in a given region, then the overall magnetic field is called as uniform magnetic field. The resultant, the cause for this is uniform flow of current. Okay, flow of current is uniform, then only we can say uniform magnetic field. Suppose if the magnetic field is varying with respect to its magnitude or with respect to its direction or with respect to both magnitude and direction within a given region, then it is non-uniform magnetic field. Then what do you mean by steady state magnetic field? Steady magnetic field. Steady magnetic field means the flow of current, the magnetic field remains constant with respect to time. Then we can call it as steady magnetic field. Clear? You need to have the difference between uniform, non-uniform and steady magnetic field. Steady magnetic field is the one where the magnetic field and flow of current remains constant with respect to varying time. Clear? To analyze magnetic field and its application in our electromagnetic wave theory concepts, we need to have certain theorems, working principles, or we can say laws, right? So under that case, the first law we are going to study is Biot Savart's law. Biot Savart's law. What this law says, Biot Savart's law. So Biot Savart's law gives the characteristics of magnetic field, developed magnetic field when a current flows through a conductor. Okay, how the Biot Savart's law states is, in order to understand that, let us consider a current carrying conductor. Let us consider a current carrying conductor. The current flowing through this wire is considered to be I. Okay, consider a current carrying conductor, a wire which carries a current of magnitude I. Okay, let us choose an elementary portion of length dl. Let us choose an elementary portion of length dl on this conductor. Let us draw a tangent to this particular conductor. Let us draw a tangent mn to this elementary length dl. So the point at this point is O. Let us choose it as O. The point at which the elementary length is chosen to be O. Let P be a arbitrary point we have chosen where the magnetic field is to be measured by using this current carrying conductor. Let us join the line OP. Let us join the line OP. The distance between O and P is R. The distance between the line O and P is R, which creates an angle theta between the line joining the points OP with the tangent drawn to that elementary length dl is theta. Got it? Let me explain this geometry again. Choose a current carrying conductor which carries a current I. Let us choose a differential length. Okay, the differential length is dl. The point at which the differential length is chosen to be O. Draw a tangent mn at the point at which the differential length is chosen. Choose an arbitrary point P at which magnetic field intensity to be measured. The distance between arbitrary point P and O is R, which creates an angle between tangent and the line joining O and P, which is termed as theta. Now, what Biot Savart's law says with this geometrical consideration? Let me explain. So at this elementary length dl, the magnetic field produced at point P is dH, differential magnetic field intensity, dH. The magnitude of differential magnetic field at point P is directly proportional to the product of current flowing through the conductor and elementary distance of the elementary length and sine of angle between the tangent drawn and the line joining the point, and inversely proportional to the square of the distance between them. This is the statement of Biot Savart's law. Let me write here the magnitude of the magnetic field intensity at point P due to elementary length dl is directly proportional to the product of current I, the length of element, that is dl, and sine of the angle between tangent drawn at the element to the line joining the element and point P, and inversely proportional to the square of the distance between them. Mathematically, which is represented like this: the magnitude of the magnetic field intensity, that is represented as dH, proportional to the product of current, this is dl, different length of the differential element, into sine theta divided by r square. Now this can be written as dH is equal to k times of I into dl into sine theta divided by r square, where k is the proportionality constant, where k is equal to 1 by 4 pi, which is called as proportionality constant. Then the above equation can be written as dH is equal to I into dl into sine theta divided by 4 pi r square. This is the magnitude of the magnetic field intensity. We know that the magnetic field intensity at point P is perpendicular to the plane of this element chosen. We have discussed already in case of electric field intensity, right? Electric field intensity and flux density always comes normal to the plane of the element we have chosen. Here also the same assumption holds good. The magnetic field intensity dH is perpendicular to the point element chosen at point O. Therefore, theta is equal to 90 degree. Perpendicular means 90 degree. Then the above equation reduces to dH is equal to I into dl divided by 4 pi r square. Right? Sin 90 is 1. Therefore, this is the equation. If the same equation is represented in terms of vector, then dH is equal to I into dl divided by 4 pi r square into a cap r, where a cap r is the unit vector. This is in terms of vector form. Biot Savart's law in terms of vector form. The magnitude of the magnetic field intensity using Biot Savart's law is given by this equation. Got it? Okay. Coming to the applications of Biot Savart's law. Applications of Biot Savart's law. First case is magnetic field intensity due to linear conductor. This is the first case, magnetic field intensity due to linear conductor. Okay, in order to have this mathematical model, let us choose a linear conductor of finite length AB. Let us choose a linear conductor of finite length AB. Okay. Let us choose a point P arbitrarily and join the center of this linear conductor to point P. The distance is assumed to be capital R. The distance is assumed to be capital R. Join these two lines. Okay, join these two lines, which creates angle theta 1 and angle theta 2 at point A and B respectively, which creates angle theta 1 at point A and theta 2 at point B respectively. Okay. Now, let us choose the elementary length at this linear conductor. Elementary length is dl and join these two points like this. Okay, join these two. If I extend this like this, if I extend this elementary length dl like this, which creates an angle theta with respect to the conductor, then this is elementary angle d theta, and this distance is r. Distance between the elementary length dl and point P is assumed to be r. The point is taken as O here. Okay. Now, which forms an angle theta, because these two are opposite angle, then this angle becomes theta. Then draw a perpendicular line like this. This is draw a perpendicular. Okay, this is the perpendicular which has been drawn. This angle is also theta. Then this is d theta, this angle is theta, this is 90 degree. Then So the distance, this distance is dl sin theta, which is given by r into d theta. This equation is obtained in our vector basics. You need to remember all those things, right? So this distance is obtained using vector basic concepts. dl sin theta, this distance is referred as dl sin theta, which is equivalent to r into d theta, because this is the radial distance which varies with respect to r. This is dl sin theta. dl sin theta is equal to r into d theta here. Now choose an arbitrary point P where the magnetic field intensity to be measured. We know that magnetic field at point P is normal or perpendicular to the plane of this linear conductor. Okay. Now consider the magnitude of Biot Savart's law. dH is equal to I into dl into sin theta divided by 4 pi r square. This is the magnitude of Biot Savart's law. We know that dl sin theta is equal to r into d theta. I is equal to r into d theta divided by 4 pi r square. Square and this r gets cancelled, then dH is equal to I divided by 4 pi into 1 by r into d theta. The above equation can be written in this form. Now by looking at this geometry, sin theta is equal to opposite by hypotenuse. Sin theta is equal to, what is the opposite one? R divided by hypotenuse r, right? Sin theta is equal to opposite by hypotenuse, right? Then sin theta is equal to capital R by small r. 1 by r can be written as sin theta divided by r by using this equation. See, if I cross multiply this r to this LHS, then sin theta divided by capital R is equal to 1 by r. Substitute into the above equation, then dH is equal to I divided by 4 pi into sin theta divided by r into d theta, right? This is the magnitude of magnetic field intensity at point P due to the elementary length dl. Now in order to get the magnetic field intensity at point P due to the entire length AB, we need to integrate all these elementary parts. Therefore H is equal to integration from theta 1 to theta 2 of all dH components. Then this can be written as integration from theta 1 to theta 2 I divided by 4 pi r into sin theta into d theta, right? So take the constants outside. I divided by 4 pi r is constant, we have taken it outside. Theta 1 to theta 2 is the integration limits, sin theta into d theta. Then H can be written as I divided by 4 pi r. What is the integration of this? Minus cos theta from theta 1 to theta 2. This can be written as, okay, let me write here, I divided by 4 pi r into, minus is taken outside, this is cos theta 2 minus cos theta 1. If I take minus inside, then the expression becomes I divided by 4 pi r into cos theta 1 minus cos theta 2. This will become reversed. If I take negative sign into the brackets, this gets reversed. This is the magnitude of the total magnetic field intensity at point P. If it is represented in terms of vector, then I divided by 4 pi r times of cos theta 1 minus cos theta 2 into a cap r. This is in terms of vector. Okay, magnetic field intensity in terms of vector format. Then coming to the special case when the length of linear conductor is infinity, when this length becomes infinitely long, then what happens to this equation? Then theta 1 is equal to 0 and theta 2 is equal to pi. This is the limiting condition. This is the special case. Okay, when the length of the linear conductor becomes infinity, theta 1 is 0 and theta 2 is pi. Substitute theta 1 is equal to 0 and theta 2 is equal to pi, then the equation for H is equal to I divided by 4 pi r integration from 0 to pi sin theta into d theta, right? Similarly, cos theta 1 is what? Cos theta 1, H is equal to 1 by 4 pi r times of, what is the value of theta 1? 0. Cos 0 minus cos theta 2 cos pi. Cos 0 value is 1. Cos pi value is minus 1. So this value becomes 1 divided by 2 pi r. H is equal to 1 divided by 2 pi r. Sorry, I divided by, not 1, this is I divided by 2 pi r for infinitely long linear conductor case. Got it? Okay, let us move on to the next concept, next application of Biot Savart's law. Magnetic field at the center of a circular current loop. Okay, so this is the next application. Let us have a geometric consideration for this. Let us have a circular current loop. The current I is flowing in this fashion. Let us choose a point, arbitrary point P at the center of this circular current loop. Let us choose a elementary distance, elementary length dl on the surface of this circular current loop. Let us join these two lines. Okay, this forms angle d theta, then this is theta, right? This forms an angle d theta. The distance is r, this is r. Here in this case, small r is equal to capital R because the radius of the circle remains same in all the points, hence small r and capital R are equal in this particular case. Then dl can be written as differential length, dl can be written as r into d theta in this case. We know this distance is equivalent to r into d theta. This distance is dependent on radial distance r and the angle, hence dl can be written as r into d theta. Now consider the magnitude of the Biot Savart's law, that is I into dl into sin theta divided by 4 pi r square. 4 pi r square. Here at this point the magnetic flux density is, magnetic field intensity is at 90 degree here. it is at 90 degree. Hence theta is equal to 90 degree. Therefore dH can be written as I into dl into 1 divided by 4 pi r square. What is dl? dl is equal to r into d theta. Therefore dH is equal to I into r into d theta divided by 4 pi r square. Square and this r gets cancelled. We are left with dH is equal to I divided by 4 pi r into d theta. Okay. Now in order to obtain the overall magnetic field intensity H at point P, we need to integrate all dH components from 0 to 2 pi. Why it is 0 to 2 pi? It starts from 0 degree and completes this circle at 2 pi. Hence, in order to complete the entire circle, we need to have the range 0 to 2 pi. Now substitute into this equation. Integration from 0 to 2 pi, dH component is I divided by 4 pi r into d theta. All these components are constant, take it outside. I divided by 4 pi r integration from 0 to 2 pi into d theta. What is the integration of d theta? Theta, apply limits. What we are going to get? H is equal to I divided by 4 pi r into 2 pi minus 0. Then H is equal to this 2 and this 2 get 4 gets cancelled, pi gets cancelled, then I divided by 2r. This is the magnitude of magnetic field intensity due to a circular current loop. If we represent this in terms of vector, then H is equal to I divided by 2r into a cap r. This is the complete representation of magnetic field intensity. Then if we go for magnetic flux density, B is equal to mu into H. Then magnetic flux density B is equal to mu into I divided by 2r into a cap r. If we represent this in vector form, this is the equation. Okay. Then moving on to the second application of this Biot Savart's law, magnetic field intensity at any point on the axis of the plane circular current loop. This is the second consideration we have taken into our discussion. Magnetic field intensity at any point on the axis of the plane circular loop. So for this case, let us choose a plane circular loop. Okay. Let us choose an arbitrary point P on the axis of this plane circular loop. Its radius is of distance r. The distance from origin of the circular loop to this point P is taken as x. Okay. Let us choose an element, differential element of length dl on top of the circular current loop. The current flowing in this circular loop is in this fashion. Let us choose a differential element of length dl on top of this circular current loop. Okay, we need to identify the magnetic field intensity at point P, which is radial to the which is on the axis of this circular current loop. Okay, now join these 2 points. So this is at a distance r, which forms an angle phi. Okay, which forms an angle phi. This is at 90 degree. Okay, this is 90 degree. Clear? Now draw a perpendicular to this. Okay, this is DH component which is perpendicular to this vector, which forms an angle phi here. If we resolve this DH component, then this can be written as DH cos phi, and this can be written as DH sin phi. If we resolve this vector DH into its components, then this can be DH cos phi, and the horizontal component is DH sin phi. Okay, with this geometry we need to find the magnetic field intensity at point P. Okay, now for that let us choose the Biot Savart Law magnitude, that is DH is equal to I into DL into sin theta divided by 4 pi r square. Okay, this is the equation. So what is theta? Theta is 90 degree. Theta is equal to 90 degree because this DH component is perpendicular to the plane of this circular current loop, hence theta is equal to 90 degree. Then DH becomes, DH is equal to I into DL divided by 4 pi r square. That's it. DH is equal to I into DL divided by 4 pi r square. Sin theta value is 1 because theta is 1. Keep this equation aside. Now looking at this geometry, if I consider the diametrically opposite point here, if I consider the diametrically opposite point to this element, here also this length is considered as DL. If I project the same vectors here with respect to the bottom element, DH cos phi will be opposite direction, will be in opposite direction. Let me write here. This will be in opposite direction. Okay, if DH component is like this, this will be DH cos phi, and this is DH, and this will be DH sin phi again. DH cos phi and DH cos phi gets cancelled because they are in opposite direction, but DH sin phi gets added due to the diametrically opposite elements. The same theory applies for the entire circular loop. See, if I consider an element here, its diametrically opposite point comes here, these two cosine components get cancelled, we left with only sine components. Okay, therefore H is equal to, in order to obtain the overall magnetic field intensity at point P, we need to integrate all DH sin phi components. Why only sin phi components? Cosine components gets cancelled due to the diametrically opposite geometrical consideration. Okay, now what is the radial distance? Now 0 to 2 pi r is the radial distance. 0 to 2 pi r is the limits, integration limits. Within this integration limits, we need to integrate DH sin phi components. We know DH value. Let us substitute here. H is equal to integration from 0 to 2 pi r. DH value is I into DL divided by 4 pi r square into sin phi. Okay. Now let me write here. Take constants outsides. I divided by 4 pi r square, integration from 0 to 2 pi r dl into sin phi. What is sin phi? With respect to this geometry, sin phi is equal to opposite by hypotenuse, that is capital R divided by small r. See, sin phi is equal to opposite by hypotenuse. Opposite is r, capital R, and hypotenuse is small r. Sin phi can be replaced by capital R by r. Therefore, H is equal to I into capital R divided by 4 pi r cube into integration from 0 to 2 pi r into dl. That's it, right? Now, H can be written as I into R divided by 4 pi r cube. What is the integration of this? L. So if I apply this, this can be written as 2 pi r minus 0. No need to write that. H is equal to I into r square divided by pi gets cancelled, 2r cube. Right? Now, look at the same right angle triangle. From Pythagoras theorem, we know that hypotenuse square is equal to sum of squares of the sides. That is, small r square can be written as x square plus capital R square. Therefore, R can be written as x square plus capital R square whole power 1 by 2. Then substitute this into the above equation, then H becomes I into R square divided by 2 into x square plus R square whole power 3 by 2. Because R cube is there, if I multiply power it by cubic root, then it is 3 by 2, whole power 3 by 2. Then if I represent this H in terms of vector, I into R square divided by 2 times of x square plus R square whole power 3 by 2 into a cap R if it is a vector. This is the equation for magnetic field intensity at point P due to a plane circular current loop. So if we want to have the equation for B is equal to mu into H. Just multiply this equation with permeability mu, we are going to get the equation for B. Then one more special case we need to consider here. If this circular current loop is having n number of turns, what will happen to this equation? If the circular current loop is having n number of turns, then this equation becomes n into I into R square divided by 2 times of x square plus capital R square whole power 3 by 2 into a cap R. This is the final equation if the loop is having n number of turns. If this current loop is having n number of turns is nothing but if it is acts like a coil of n number of turns, then this equation holds good, where n represents the number of turns in the coil. Okay? Another special case you need to consider here. What happens if I choose this point at the center of this loop? Okay, we need to get back with the same equation which we have derived previously, right? If this point is chosen at the center of this current loop, then x is 0. The value of x is 0, right? if I choose x is equal to 0, then this equation becomes r cube, right? This equation, in this equation, x becomes 0 means if x is equal to 0, that means at what point x becomes 0? If I choose this point at the center of this circular current loop, x becomes 0, then this equation h is equal to I into r square whole divided by 2 times of r square whole power 3 by 2. 2 gets cancelled, r cube, then h is equal to I divided by 2r into a cap r. See, we have got the same equation which we have derived previously for circular current loop, where the point P is kept at the center of the circular current loop. Okay, got it? Okay, let us move on to the next application, magnetic field intensity at a point on the axis of a solenoid. In the previous case, we have considered only a planar circular loop, but here if we consider a solenoid here, in this case, so we have n number of such planar circular loops here. If I take a segment of this solenoid, then this part becomes, the thickness of this particular section is taken as dx. Okay, the thickness of this elementary part considered out of this solenoid of length L. This length of this solenoid is assumed to be L. Okay, the elementary cross sectional area width is considered to be dx. Now let me explain the geometry. The arbitrary point P at which magnetic field intensity to be measured is taken at the axis of this solenoid. Okay, which makes an angle phi with respect to the top surface of this coil, which makes an angle phi 2 with respect to the right edge of this solenoid, and phi 1 with respect to left edge of this solenoid. See, this is the left edge, this is the right edge. The angle formed with respect to the radial axis is phi 1 and phi 2 with respect to left and right edge of the solenoid respectively. The angle phi has been made with respect to the top end of this coil, circular planar coil, which we have chosen. Now the distance between point P and center of this coil chosen is assumed to be x. The distance from point P and top end of this assumed coil is taken as r. Now this forms the right angle triangle. Which is very similar to the second application which we have derived for planar circular current loop. Okay, now the equation which we have derived for circular planar current loop has been considered as elementary part here. Therefore dH is equal to n times of I into r square divided by 2 times of x square plus r square whole power 3 by 2. See, in the previous case this has been equivalent to the overall magnetic field produced by a single circular current loop, a single planar circular current loop. But here that single planar circular current loop is a part of a big solenoid of length L. Hence the H becomes dH here in this case. Keep that in your mind. Now what is N? The number of turns. Capital N is the overall number of turns of the solenoid, but we need to have the number of turns present within this elementary distance dx, and small n can be derived out of capital N, that is total number of turns of the solenoid divided by total length of this solenoid into this small distance, small area dx. So small n can be written as dh is equal to n into dx into I into r square whole divided by 2l x square plus r square whole power 3 by 2. By looking at the geometry, by looking at this right angle triangular geometry, r can be written as r cosecant theta, cosecant phi, sorry, not theta, r cosecant phi. See, this r distance can be obtained by r cosecant phi. We know that from Pythagoras theorem, what it says from Pythagoras theorem, we can say hypotenuse r square is equal to x square plus capital R square, right? R square is equal to x square plus capital R square, we can obtain that. Then what about x? X is equal to, by looking at the same right angle triangle, x can be written as r cot phi. You need to remember all the trigonometric identities of a right angle triangle, okay? We cannot keep on telling the same things. R, the hypotenuse of this right angle triangle can be obtained as r cosecant phi. This side x can be obtained by r cot phi, okay, by using trigonometric identities. Now we need to have dx component here, therefore differentiate this equation. Then dx is equal to minus r cosecant square phi into d phi. R is constant, take it outside. Differentiation of cot phi is minus cosecant square phi into d phi. Substitute these two components into the above equation. Therefore, what we are going to get, dh is equal to n into minus n into r into cosecant square phi into d phi. Okay, see, n remains same. Instead of dx, I have substituted this entire term into I into r square whole divided by, this whole thing can be written as r cube, okay, r cube. R square into r, this becomes r cube. Then 2l into x square plus r square, x square plus r square. See, this r can be written as what? R cosecant phi. This x square plus r square is equal to x square plus capital R square whole power 1 by 2 is equal to r. R cube can be written as whole power 3 by 2. This whole term can be written as r cube. Okay, see, x square plus r square whole power 3 by 2 can be written as r cube by using this identity. Then dh can also be written as minus n into r cube into cosecant square phi into d phi into I divided by 2l. R cube means r cosecant phi whole cube, right? R cosecant phi whole cube. What we are getting here, r square cosecant square gets cancelled, then dh is equal to minus, so r cube gets cancelled, n into I divided by 2l into d phi into 1 by cosecant phi can be written as sin phi, right? We left with 1 cosecant phi, 1 by cosecant phi is sin phi, right? So we left with this quantity. Then dh is equal to minus n into I divided by 2l into sin phi into d phi. In order to obtain h, what we need to do? We need to integrate the entire thing from phi 1 to phi 2, all dh components. This can be written as minus n into I divided by 2l integration from phi 1 to phi 2 sin phi into d phi. After integrating this, what we are going to get? H is equal to minus n into I divided by 2L. Integration of sin phi is minus cos phi. Minus cos phi. Minus cos phi. Minus into minus plus. H is equal to n into I divided by 2L. So from phi 1 to phi 2. So cos phi 2 minus cos phi 1. This is the overall equation for magnetic field intensity due to a solenoid of length L. Okay. Now, if the length L is equal to infinity, if the length of this solenoid is of infinitely long, what will happen to this equation? In this equation, phi 2 becomes, phi 2 becomes 0 and phi 1 becomes pi. Then the above equation can be written as H is equal to n into I divided by 2L into cos 0 is 1, right? Cos 0, phi 2 becomes 0, means cos 0 1 minus of minus, that is minus 1. What we are going to get? H is equal to n into I divided by L. That's it. This is the equation for magnetic field intensity due to infinitely long solenoid where the point P is chosen on the axis of the solenoid. If we want to have the equation for B is equal to mu into H. Therefore, B can be written as mu into n into I divided by L into A cap R. It is in vector form. Suppose if the solenoid, if the point P is taken on the axis and phi 1 becomes pi by 2, what will happen to this equation? If phi 1 becomes pi by 2, what will happen to this equation? Cos 90 is 0. Then this equation becomes, what happens to this equation? N into I divided by 2L, that's it. Okay. When phi 1 becomes pi by 2 means when point P is at the end of the solenoid. When phi 1 becomes pi by 2 means this point P is at end of the solenoid. When this point is at the end of the solenoid, this phi 1 becomes pi by 2. Let me write here. If point P is at the end of solenoid, then phi 1 is equal to 90 degree. Then equation for H becomes, look at this equation. When phi 1 is equal to 90 degree, cos 90 is 0, phi 2 remains same as 0, cos 0 is 1. Therefore, H is equal to n into I divided by 2L. That's it. This is the equation for another special case. There are two special cases here. When the solenoid is of infinite length, then phi 2 becomes 0 and phi 1 becomes pi. Under this circumstance, magnetic field intensity H is equal to n into I divided by L. When we move this point P at the end of this solenoid, okay, then phi 1 becomes 90 degree and phi 2 remains same as 0, right? Under this circumstance, H is equal to n into I divided by 2L. So these are the three important applications of Biot Savart's law. Let me recall what we have studied in this particular session. We have seen the effect and cause of magnetic field and magnetic flux density. We have seen the symbols and the relationship between magnetic field intensity and magnetic flux density and their units, right? So we have derived the mathematical equation for Biot Savart's law. We have done the statement of, we have understood the statement of Biot Savart's law by applying Biot Savart's law to the different considerations. One is linear conductor, another one is circular loop, another one is circular loop with n number of turns, and another application is a solenoid of n number of turns. Okay, so with this, let us conclude this particular session. Hope you have understood the Biot Savart's law and its applications. In the further classes, we can go for few numerical problems on this, and we can move on to the Ampere's law of magnetic field intensity. Okay, thank you.